it going? Back with day 52. I saw a lot of excellent work today in class, tackling some of those really tough related rate problems. The key here is that you never give up, right? Anytime you're in a problem and you feel like you're stuck, don't give up. Think of what else you can do. Think of what else you can use. Okay, I'm back at you today with a new problem. It's a little wordy, so I'll give you, just pause it quick and go ahead and write this question into your notes. I know it's kind of wordy, but it'll be important to have it written down so when you review it later, you know what was going on. Okay, so here we have a 17-foot ladder is sliding down the side of a building. At the instant the top of the ladder is 8 feet above the ground, and the foot of the ladder is 15 feet from the base, the top of the ladder is sliding down the building at a rate of 3 feet per second. At what rate is the foot of the ladder moving relative to the ground at that instant? Okay, a lot going on here. This is a problem where it might be a good idea to make a sketch and see what the heck is going on. So here's what we have. I'm going to go ahead and sketch a little picture with this. Okay. Here's my building. Here's the ground. And I have a ladder that's sliding down this building, right? So that ladder, right, maybe somebody was trying to work on their house and it was icy out. Uh-oh, the ladder starts slipping. What's going to happen? First thing we should notice here is, obviously we're forming a right triangle here. What I want to do is figure out what are my variables in this problem. Now, a lot of the right triangles we've been working with, all three sides of the triangle are changing. However, that is not the case here. Because think about this ladder, right? The ladder is the hypotenuse of this triangle. That ladder is 17 feet, and it's not changing, right? The ladder isn't growing or shrinking, right? The ladder is staying the same. So I'm not going to label the hypotenuse with a variable because it's not varying, right? It is a solid ladder that is 17 feet. It's going to be 17 feet before, after, and during this fall. So I'm going to go ahead and label that 17. What I do want to come up with is that distance between the foot of the ladder and the building, that will be changing. That distance between the top of the ladder and the ground, that distance will be changing. So I want to come up with variables for those. So here's what I'm going to do. I'm going to choose the letters x and y because it looks like an xy axis to me. So I'm going to call this distance x. I'm going to call this distance y. Okay. So we have our x and y. Now, even though, at the instant we know what x is and at the instant we know what y is, those will be changing, so I have to give them letters because they're variables. The ladder is going to be 17 feet, and it's always going to be 17 feet, right? So I'm just going to call it 17. That's different than what we've worked on before. Okay, so now I want to go through and make my no column. I'll do it up here just to save space. So I know that the ladder has a length of 17 feet. Right, that's pretty clear in my diagram. I'm also not giving it a variable, so I'm not going to write that in my no column. I'm just going to use my picture for that. So let's talk about x and y. It says at the instant the top of the ladder is 8 feet above the ground. That 8 feet is not a rate, that is simply an amount. So which letter is going to be equal to 8? Well, it's talking about above the ground height. That's going to be our y. So right away I know y equals 8. Okay. It says the foot of the ladder is 15 feet from the base of the building. Look at that unit, 15 feet. That's not a rate, that's an amount. So I'm going to put x equals 15. And it says, and the top of the ladder is sliding down the building at a rate of 3 feet per second. So there's our rate. And it says the top of the ladder is sliding down the building at a rate of 3 feet per second. Here's the really important piece. I'm going to use kind of a different color here to help us out. The top of the ladder, as this ladder is falling, right, the top of the ladder is going down. What about the foot of the ladder? Which direction would that be moving? Well, that obviously has to be moving to the right. We know today from that Adriana and Brandon problem that the direction that these things move is very important because it can help us determine the sign. Now I'm going to ask you, right, the top of the ladder is moving down at a rate of 3 feet per second. So that's obviously talking about dy dt. I want you to answer this question to yourself. Is dy dt going to be 3 or negative 3? Well, to answer that question, I ask myself this. Is y, that part of my triangle y, is it getting smaller or is it getting bigger as this ladder is falling? Well, clearly it's getting smaller, right? You know, a second later, this ladder is going to have slid a little bit more and y is going to be a smaller number. So the rate of change of y here has to be negative. So I'm going to say dy dt equals negative 3. Some of you guys did a really good job of catching that right away with the Adriana and Brandon problem. If you didn't catch it right away, that's fine. As long as you catch it by test day, right? So dy dt equals negative 3. Right, so that's the rate of change of y. What I want to figure out, my need, is at what rate is the foot of the ladder moving relative to the ground at that instant. So I want to know the rate of change of x here. So I need dx dt. Okay, so I need dx dt. Now I can answer this question right away. Should dx dt be a positive number or a negative number? Well, clearly, is x getting bigger or smaller in this scenario? Well, x is going to be getting larger. So dx dt should be a positive number. Hopefully it comes out positive. BTW, if it comes out negative, I know something's wrong. Okay, now I need an equation that relates these three sides. Well, whenever I have the three sides of a right triangle, my equation is always going to be, or often going to be, the Pythagorean theorem. So in this case, I know that x squared plus y squared has to equal 17 squared. So that's my equation. That's the equation I'm going to derive, because it's going to give me, when I derive it, it's going to give me dx dt. I'm going to have to know x, which I already do. I'm going to have to know y, which I already do. And I'm going to have to know dy dt, which I already do. So this thing should work out quite nicely here. So I'm going to do the problem down here. So right, I'm deriving this equation. What's the derivative of x squared? Well, that's 2x. But don't forget, the most common mistake people make on this is they forget to tack on dx dt. So 2x dx dt plus 2y dy dt equals, what's the derivative of 17? Please don't say 2 times 17. Right? 17 squared is simply a number. The derivative of a number is always 0. So that's kind of nice. It just goes away. Okay. Now you may be asking yourself, can I still cross off those 2's? Can I still get rid of those 2's? I don't know. What do you think? Is every term divisible by 2? Well, obviously the 2 on the left are divisible by 2. Is 0 divisible by 2? Yeah, it just made 0. So to make life a little bit easier, I'm just going to cross off those 2's. I can do it because really what I'm doing is I'm dividing everything by 2, right? Again, without a calculator, little steps like that can help us to do this right. So I get x dx dt plus y dy dt equals 0 divided by 2 is still 0. Okay, so what goes in for x? Well, this is why I make a no column, right? So I don't have to reread the problem to figure out all my stuff, right? X equals 15, plug it in. Dx dt, I don't know, that's what I need. So I'm going to leave it as dx dt. Plus y. Well, I can look at my no column. Y is 8. And dy dt is negative 3, right here. Okay, I'm just going to simplify this thing. I got 15 dx dt minus 24 equals 0. Now I'm going to add 24 over. I get 15 dx dt equals positive 24. And now I'm going to divide both sides by 15. So I get dx dt equals 24 over 15. Both of those divided by what? 3. 24 divided by 3 is 8. 15 divided by 3 is 5. So I get 8 feet, 8 fifths. My unit, x, is a distance. In this problem, I used feet per second. Now, a little analysis time. Was my dx dt positive like I thought it should be? The answer is yes. My next question for you is, which one is moving faster? The top of the ladder or the foot of the ladder? Which one has a bigger speed? Well, the speed of the top of the ladder would be 3, right? Speed is always positive, absolute value of velocity. So the speed of the top of the ladder is 3. The speed of the bottom of the ladder is 8 fifths, which is less than 2, so definitely less than 3. So the top of the ladder is moving a little faster than the bottom of the ladder is here. Okay? Now, let's see if I have time. Ooh, good, I do. Now I want to know extension time. I want to know what is the rate of change of that angle at that instant. So I want to know what is the rate of change of the angle theta, the angle between the ladder and the ground. What is the rate of change of that angle at that instant? Now think, would that angle be increasing in size or decreasing in size? Well, this ladder is falling down to the ground, right? So theta here should be getting smaller as this ladder is falling down. So when I find the rate of change of theta, right, d theta dt, I should end up with a negative number. If I don't, I know I did something wrong. Okay? So here's what we're going to do. I'm going to just kind of redraw this picture quick so I can reference it a little bit better. Okay, so I'm going to write down everything I know. Well, I knew that y was 8. I knew that dy dt was negative 3. I knew that x was 15. I just found that dx dt was, what did I get? 8 fifths, I think? Yep. I can now move that to my no column, right? Because I now know it. What I need now is d theta dt. Okay, so I need to know the rate of change of that angle theta. I also need to figure out what equation could I use that involves theta. And if I can think of more than one, then I really want to think about which one's going to be easiest. Okay? Well, if we need to solve for theta, right, our trig functions always involve theta here. So I have a few options. I could write an equation for sine of theta, I could write an equation for cosine of theta, or I could write an equation for tangent of theta. But think, we're going to be deriving this. The derivative of sine theta is cos theta. That's nice. Derivative of cos theta is negative sine theta. That's okay. Derivative of tan theta is secant squared theta. Yeah. Okay, I don't want to do secant squared. Right? I could, but I don't really want to do it that way. So, here's what I'm going to do. I'm just going to pick one and hope it works out. It turns out that you could use any of the three here and it's going to work. So what I need to do is I need to write an equation for, I'm going to use sine. Let's make life as easy as possible. So I want to write an equation, right? Sine theta is not an equation, that's an expression. What would sine theta equal? Well, think back to SOHCAHTOA, right? SOHCAHTOA tells us all of our trig functions we need to know. Sine, so, opposite hypotenuse, sine, opposite hypotenuse. So sine of theta is going to be opposite over hypotenuse. What's the opposite from theta? Well, that would be y. What's the hypotenuse? That's 17. The other nice thing about using sine or cosine here is it involves the constant, which just makes the derivative a little bit easier. Now, one of the things we worked on today is making this as easy as possible to do a derivative. Right? When I see y over 17, right, I don't want to have to do a quotient rule. And I don't have to. And the easier way to see this is if I write it in ax to the n, or in this case, ay to the n. So here's how I'm going to write this. Y over 17 is exactly the same as 1/17 y. To me, it's way easier to derive 1/17 y than it is y over 17. Because, it's the same thing, right? But I like to see a coefficient and then a variable. Okay, so here's my equation. Now I want to do the derivative of both sides, remembering that I have to follow all my rules, and I have to tack on d whatever dt. So what's the derivative of sine theta? Well, that would be cosine theta. Hey, that's easy. But I need to tack on d theta dt. Cosine theta d theta dt. That has to equal, what's the derivative of 1/17 y? Well, that's a linear derivative, very simple. It's just the coefficient 1/17. Well, what do I need to tack on? I need to tack on dy dt. Now, after I do the derivative, I want to plug in. I'm going to plug in from right to left here, just because I'm curious about that cosine theta. Okay. So, dy dt, what's going in for that? That's -3. 1/17 is just a constant. I'm going to rewrite it. D theta dt is unknown, and that's okay because it's in my need column. Cosine theta. Oh, what is that? Right? Now remember, we can plug in the values we need here. Cosine theta. Think about that definition, cosine. So we use that to write our initial equation. Cosine is adjacent over hypotenuse. So cosine is x over 17. But now I can plug in the value for x. What was x's value? Well, it was 15. So I know that cosine of theta is always equal to the adjacent side, which is 15, divided by the hypotenuse, which is 17. So cosine theta, right, here's where I did this. Cosine theta equals 15 over 17. So I just sub that in. Cleaning up the right side here, I get 15/17 d theta dt equals -3/17 on the right side. Now I want to isolate d theta dt, so I'm going to go ahead and multiply both sides by the reciprocal. Multiply both sides by the reciprocal. Nice thing is there, my 17s cancel, right? I get d theta dt. D theta dt equals, the 17s cancel there. These I can reduce here. 15 becomes 5. So I can divide by 3. And the 3 becomes 1. So I get an answer of -1/5. What about the unit? How do I measure angles? Now, the geometry student in you might say, degrees is the answer. That's not true. Not in big boy math, right? In big boy math, we measure angles with radians. So our answer is -1/5 radians. Per second. And there we did it. We solved it. Now, I got 4 minutes before the next class comes in. I just want to show you that if we would have chosen a different equation, it could have worked. If I would have chosen cosine theta to write my initial equation here, instead of sine of theta equals y/17, I could have used cosine theta, and then I would have had to do x/17. So just check this out. I'm going to do this kind of fast, so don't worry about it. Cosine theta, then I could also think of as 1/17 x. I always like to make this move right here to make my derivative easier. Now, what is the derivative of cosine theta? Well, we all know that. It's negative sine theta, but I got to tack on d theta dt. That equals 1/17. Right? The derivative of 1/17 x is 1/17, but I got to tack on dx dt. Okay? Now I'm going to plug in all the values that I know. Let's start at the back. dx dt I know is 8/5 times 1/17, right? d theta dt is unknown. I mean, we know now it's -1/5, but hopefully that'll come out anyways. Now I have to do negative sine of theta. So I can put my negative out there. Now sine of theta, now I can plug in my real numbers for it. Sine is opposite over hypotenuse. So it's y/17, right? y/17. But I know that y's value is 8. So it's 8/17. And it ends up being -8/17. Okay? So, to make this a little bit easier, I'm not going to simplify this right now because it's going to come out in the wash. What I'm going to do is I'm going to multiply both sides by the reciprocal, which would be -17/8. So I'm going to multiply this by -17/8. And look at what beautiful thing happens here, right? That all goes away. I get d theta dt equals. I'm going to cross off my 17 and my 17. That's why I didn't do 17 times 5. I'm going to cross off my 8 and my 8. And what am I left with? Multiply all the top, I get -1. Multiply all the bottom, there's only a 5. And I still get -115 radian per second. By the way, you can abbreviate radian RAD. That's fine. So I get the same answer whether I use sine theta or cos theta. I think it might have been a little bit easier there to use sine theta, but it's up to you. And that is it for today. We'll look at some of these problems like this tomorrow in class. Awesome job today. See you later. 2 trains. Bye.